morning, dear students. Myself, Dr.V, Priya, working as Associate Professor in Chemistry, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. In today's class, we are going to learn about conducting polymers. That means some kind of polymers, they are able to conduct electricity. Their classification, how many types conducting polymers are classified, and then even we can do doping for conducting polymers for enhancing its conduction capacity. So let us see how that doping will be continued in the case of polyacetylene. So let us start with introduction to conducting polymers. So as I told you, some kind of polymeric materials are able to exhibit conduction when they are having availability of free electrons. That means most polymeric materials are poor conductors of electricity because of non-availability of free electrons in the conduction process. In the past few years, polymers have been synthesized which possessed electrical conductivities on par with metallic conductors. Such kind of polymers are what we call it as conducting polymers. Some kind of, as I told you, some kind of polymers which are existing, which can be synthesized, are able to exhibit conduction purely due to availability of either free electrons or ions. Because of that mobility of ions or electrons, it is able to exhibit conduction. Such kind of conductors are named to be, such kind of polymers are named to be conducting polymers. So conductivities are as high as 1.5 into 10 power 7 ohm inverse per meter. So have been attained in these polymer materials. So if you notice these kind of conducting polymers, they are able to exhibit the conductivities approximately in a range of 1.5 to 10 power 7 ohm inverse per meter. So these conducting polymers are carbon based long chains consisting of simple monomer units and are capable of conducting electricity along the main chain, which are able to conduct the electricity along the carbon main chain. To exhibit the conduction property, the polymers must have following satisfactory conditions. One is conjugated electrons, that means presence of conjugated electrons, or they should have a positive or a negative charge. They should have a positive or a negative charge, or at least a conducting element being mixed. A conducting element being mixed with it, which enables the current to travel along the chain. So let us see. So these are the few examples which were mentioned here. Phenol formaldehyde, and it is having a conductivity in a range of 10 power minus 10 to 10 power minus 10. Polymethyl methacrylate, it is having a conductivity less than 10 power minus 12 ohm inverse meter inverse. And the nylon 66 is able to exhibit a conductivity in a range of 10 power minus 12 to 10 power minus 13. And then polystyrene, which is having a conductivity of less than 10 power minus 14 ohm inverse meter inverse. Polyethylene is able to exhibit a conductance or electricity in a range of 10 power minus 15 to 10 power minus 17. And then polytetrafluoroethylene less than 10 power minus 17. So these are basing on their weight or conductivity ranges. So these examples were mentioned here. Electrical conductivities of some polymers. Let us go with the classification of conducting polymers. Into how many types conducting polymers were classified. So generally these are classified into two types, ICPs and ECPs. ICPs are intrinsically conducting polymers and ECPs are extrinsically conducting polymers. So coming to ICPs, again we have a subclassification, that is conjugated conducting polymers or conjugated ICPs, or we will call it as ICPs that are having conjugation of pi bond or conjugation of pi electrons. And then second one, it is doped conducting polymers or doped ICPs. Again we have two types, p doping and doping. And coming to the second category, that is ECPs. Full form of ECP, it is extrinsically conducting polymers. It is of two types, conductive element filled polymers and then blended conducting polymers. So let us start with ICPs first. ICPs which are having conjugation of pi bond. Start with this one. So these are a type of ICPs, or we will call them as intrinsically conducting polymers, which are having a conjugation of double bond, that is nothing but alternating double bond presence will be there in the polymer backbone. So because of which it will have delocalized electrons presence, which are able to form valence band as well as conduction band. So these electrons as the presence of delocalized electrons is available in the polymer backbone, and these electrons are able to get excited easily under electric field, and as a result the conduction takes place along the polymer backbone. So presence of this conjugated pi electrons, and the length of conjugation in a polymer gets increased. As a result, its conduction also gets increased to a larger extent. So example for this type of things are polyacetylene. So if you notice the structure of acetylene, what is acetylene? Acetylene, it is an alkyne, and it is having 2 carbons, and these 2 are linked like this way, CH triple bond CH. So this is the structure of acetylene. If it is subjected to polymerization, n moles of acetylene it is taken, and if it is subjected to polymerization, then what will happen? Here if you notice the structure, it is having 2 pi bonds. These are 2 pi bonds and 1 sigma bond presence it is there. So because of these presence of pi bonds, if they involve in breaking process, as a result a new bond formation will take place. So if you notice this pi bond, it is involving in breaking process, as a result each carbon will acquire a new sigma bond, that means CH double bond CH and then a bond CH double bond and CH. Like this chain will continue. So this is what we call it as polyacetylene. So this is acetylene, and then if it is subjected to polymerization reaction, polyacetylene will be the result. In the similar manner, here some examples were mentioned which are having a conjugation of double bond in the polymer backbone. So this is polyacetylene. Just now I have shown you how its formation will take place by involving in polymerization reaction. And another example, it is polyaniline. So it is obtained by subjecting aniline to polymerization reaction. So polyaniline will be the result, and then polypyrrole, and then polythiophene, which is if sulfur presence is there, then we will call that one as thio, and then poly 3,4 ethylene dioxythiophene, that is P dot, and then PPV, polyphenyl vinylene. So these are the few examples for ICPs, or we will call them as intrinsically conducting polymers, which are having polymer backbone in the long chain of that compound. So what is the next one? So as I explained you the examples of conjugated ICPs, here I have written the reactions also. Just now we discussed about this acetylene. This is acetylene, which is example for alkane. When it is subjected to polymerization reaction, as I told you, one of its pi bond gets involving in breaking process. As a result, it is able to convert into its corresponding polymer, that is called polyacetylene. And if you notice this structure, it is what we call as trans structure of polyacetylene. Similarly, aniline, this is the structure of aniline, and n moles of aniline, it is acting like a monomer and subjected to polymerization reaction, then it is able to form polyaniline, or we will call it as emeraldine base. Similarly, this is one more example, pyrrole, or we will call it as polypyrrole formation, and then if nitrogen it is there, we will call that one as pyrrole. It's a 5-membered ring, and after subjecting to polymerization reaction, it is able to convert into corresponding polypyrrole. So all this type of conducting polymers formation is possible because they are having conjugation of double bond presence in their polymer backbone. So that's why they are examples for conjugated pi bond presence in intrinsically conducting polymers. So coming to the next second type of ICPs, intrinsically conducting polymers, that is doping. Doped ICPs. Doped ICPs are nothing but ICPs when subjected to doping. It will be done in 2 ways, P doping and N doping. So let us see how it is possible. So I am going to consider the example of polyacetylene. In which we are going to undergo this polyacetylene into doping process, and as I told you, it is of 2 different types, P doping and N doping. So CCP, that means conjugated conducting polymers, as they have very low conductivity rates, that is like they are behaving like semiconductors, so low ionization potential. Because of all this kind and high electron affinities, because of all these kind of properties, So they need to be either oxidized or reduced for increasing or enhancing its conductance capacities. They are subjected to doping process for enhancing its conduction. So this can be done either by involving them in either oxidation or reduction. So consequently, the conductivity of CCPs can be increased by creating either positive or negative charge on the polymer backbone, either by subjecting to oxidation or reduction. So this kind of technique is what we call it as doping. And doping can be done in two different ways, p-doping and n-doping. So what do you mean by doping? Generally, this intrinsically conducting polymers are able to exhibit some kind of conductance which is very poor. So if you want to increase its conductance either by subjecting that polymer into oxidation or reduction, so that it is able to enhance or increase its conductivity range. So this process is what we call it as doping, and this doping, it is of how many types? Two different types. What are they? P-doping and N-doping. So let us see this P-doping in polyacetylene. So what is P-doping? In this type of P-doping or process of P-doping, that ICP, that is intrinsically conducting polymers, are treated with Lewis acids. What do you mean by Lewis acid? Lewis acids are considered as electron pair acceptors. Electron pair acceptors. These are able to accept electron from the donor compound. So thereby what will happen? Oxidation will take place, and as a result they are able to form a positive charge in the polymer backbone. Some of common P-doping agents are ferric chloride, iodine, bromine, ASF5 and then PF6. So oxidation of polyacetylene, if you notice, oxidation of the polyacetylene, if you notice, see this is polyacetylene. When it is subjected to a treatment with a Lewis acid, say for example I have considered ferric chloride, then it is able to form a positive charge because it is electron pair acceptor. So it is able to accept electron pair. This is electron pair acceptor. So it involves in what? Oxidation. Oxidation, that means this polymer is able to release electrons. So that released electrons were accepted by Lewis acid. So as a result oxidation takes place, and if you notice the polymer backbone, negative positive charge and positive charge in the polymer backbone is able to be created. So if you notice the polymer backbone, positive charge will be created, right? So see the another example, this if this polyacetylene, it is subjected to treatment with another Lewis acid, that is iodine, it is also involving in oxidation, so that in the polymer backbone, if you notice, positive charge will be created. So because of the presence of that positive charge, and it is involving in conjugation, so as a result what will happen? These type of ICPs are able to increase their conductivity range. So let us see the mechanism part, how it is going to take place in the case of polyacetylene when subjected to P-doping. So in P-doping, oxidation process is able to form a delocalized radical ion, that is called polaron, and here if it is followed by second time oxidation, this polaron is able to yield two positive charges, or we will call them as bipolaron, on the polymer backbone on each chain, which are having mobility, and when some potential it is applied, so these positive charges move along the chain and they are able to show higher conductivity. So if you notice the mechanism part, this is the structure of polyacetylene. If it is subjected to one time oxidation, so in step 1 it is subjected to oxidation. So as a result, what is happening in oxidation? Loss of electron is nothing but oxidation. So for this to take place, this polyacetylene is to be treated with a Lewis acid. So this is an example for Lewis acid. On subjecting to a treatment with Lewis acid, so this is able to release one electron, that is involving in oxidation. Then what will happen? So as it is able to release one electron, if you notice initially it is having a double bond presence here. So that bond, it is able to involve in breaking process because of this Lewis acid. First one electron it is able to release. So this carbon is acquiring a positive charge. And then here one dot we need to mention. That means this carbon is having one free radical. That's why it is named as radical cation. Radical cation, or we will call it as polaron. So and then if it is subjected to second time polymerization reaction, and then one more free radical presence is there in the initial step. So that also it is able to lose, so that it is able to get two positive charges. That's why it is called as a dication or bipolar ion. So, and then in the next step, after the formation of this dication or bipolar ion, this charge is involving in segregation, or we will call it as segregation of cations. So, if this bond it is shifted towards this carbon atoms, and then this bond is going to shift towards this carbon atoms, then what will happen? This charge separation takes place. Segregation of this cation, that is positive charge, takes place. As this bond it is shifted, this carbon will acquire a positive charge. So here in this last step, we are getting a positive charge. If this bond is shifted towards here, and this carbon will have a positive charge. Deficiency represents positive charge. So this is what we call as soliton pair. This is what we call it as soliton pair, or we will call it as p-doped polyacetylene. So I am explaining once again. When this polyacetylene it is subjected to oxidation in first step, it is able to lose one electron, and that electron it is gained by Lewis acid. In this case, we have taken iodine. So as a result, you can notice the formation of cation along with that this carbon, because this double bond it is present between two carbons. This is one carbon and this is another carbon, right? So one of the two carbon atoms will acquire a positive charge and other carbon will acquire a radical cation. So that's why it is named as polar ion or radical cation. So what happens in the next step? This radical cation, if it is subjected to second time oxidation, this radical whatever it is present on the carbon, that will be lost. That means it is able to release the electron. Radical is representing single electron. So that will be lost. So as a result, both the carbon atoms will acquire a positive charge. So that's why it is named as dication or bipolar ion. So as this dication formation takes place, these are involving in segregation of cations in the next step. Let us see how it will happen. So if this double bond we are going to shift towards this side, that means this bond it is going to shift towards this side, that is conjugation. So as a result, this carbon will acquire a positive charge. So that is represented here. And then here we have a positive charge, that means it is electron deficient. So it is seeking electrons from the next carbon atoms which is rich. So in this case, it is having one pi bond. So this pi bond, if it is shifted towards this carbon, then this carbon atom will acquire a positive charge. So in this case, that positive charge it is represented. So in this way, this positive charge will segregate along the polymer backbone, thereby conductivity of polyacetylene can be increased. So this is what we call it as p-doped polyacetylene. So this is the mechanism that is involved in doping, that is p-doping in the case of polyacetylene. So let us go for the second type, N-doping in polyacetylene. If you notice, this N-doping of polyacetylene takes place when this polyacetylene, if it is subjected to treatment with Lewis base. So same polyacetylene I am going to consider in this case also, same ICP, and by subjecting that one to reduction by using a Lewis base. Lewis base is electron pair donor. So if it is able to release the electrons, then the gain of electrons is nothing but reduction. So then this ICP, that is polyacetylene, is able to gain that electron by involving in reduction. So thereby it is able to create a negative charge in the polymer backbone. So as a result, its conduction will be increased. So if you notice the structure, this is the structure of polyacetylene, and on subjecting to reduction, that means it is able to gain one electron. So for that we need to use one Lewis base, that is electron pair donor. So in first step only one electron will be donated. So that is gained by the polyacetylene. So as it is taking one electron, it is able to acquire negative charge. It is highly rich. That's why it will acquire a negative charge. So that's why it is named as radical anion, or we will call it as polar ion. So in the next step again, it is subjected to second time reduction. Then this is able to release one more electron, and that electron will be gained by this polymer, that is polyacetylene. As a result, this carbon will acquire a negative charge. This here. And then what will happen in this case? As we are getting two different ions, that are anion, or we will call it as bipolar ion of polyacetylene, and presence of this negative charge, if it involves in segregation of anions, then what will happen? Let us see. So as we know that conjugation of pi bond, it is possible in the case of polyacetylene backbone. Then if you, here it is negative, that means electron rich. If I shift this negative charge, that means electron pair, towards these two carbon atoms, then these become electron rich, that's why negative charge. So this bond will be shifted towards next two carbon atoms. Same thing with this anion. If it is shifted here, this bond will be shifted to this next carbon atoms. So as a result, if you notice the structure, so in this case, two charges will be produced on different carbon atoms, so that segregation of anions has been taking place in the polymer backbone. So this is what we call it as soliton pair, or simply we will call it as end-doped polyacetylene. So this is nothing but end-doped polyacetylene. So by involving in this kind of mechanism, end-doping also takes place, so that that polyacetylene is able to increase its conduction capacity. So let us see the another type of conducting polymers, that is extrinsically conducting polymers. So what are extrinsically conducting polymers? In the previous case, if you notice, intrinsically conducting polymers. Intrinsically conducting polymers, ICPs. So if you notice these ICPs, internally we are bringing changes. Internally we are bringing changes by adding either Lewis acid or Lewis base, so that internal changes will take place in the polymer backbone, so that their conduction will be increased. If it is for the case of extrinsically conducting polymers, externally we are adding. So as an additive, externally we are adding one kind of additive or a chemical to the ECPs, that is extrinsically conducting polymers, so that their conduction will be enhanced. So basing on this logic, it is again classified into two different types. They are conductive element filled polymers. So in this conductive elements, we need to consider like examples. Few examples include carbon black. Carbon black, it is a material that is produced by incomplete combustion of heavy petroleum products like coal tar, vegetable matter, etc. And then metallic fibers and metallic oxides, anything we can consider. So these will play the role of conductive element. These are able to impart a conduction property to the polymers that we have considered. When these were added in proper proportions to the ICPs, then conducting polymers, then they will able to increase the conduction capacity of this conducting polymers. So these polymers possess reasonably good bulk conduction, and they are mechanically durable, strong, light in weight. These are available at low cost and easily processable in different forms and shapes. And coming to the next second type of extrinsically conducting polymers, they are called blended polymers. So in this type of polymers, what we are going to do is, conventional polymers are blended with conducting polymers, and due to the physical or chemical changes that are taking place, overall conduction will be substantially increased. So as a result, these will improve their conductivities. So such kind of polymers can be easily processed, and they possess very, we can say, better physical, chemical and mechanical properties, and overall reduction in the cost also will be another consequence. Say for example, 40% polypyrrole when it is blended with any conventional polymer, that means 60% we have to take the conventional polymer. So for improvising its properties, it is to be blended with 40% polypyrrole, so that its conduction capacity will be increased. And coming to the applications of conducting polymers, these are having a lot of applications. Among those, few are mentioned here. In rechargeable batteries, these are used as a source for supplying a current density up to 50 milliamperes per centimeter square, which are very small in size, like button type batteries, but these are able to produce conduction capacity. And in analytical sensors like pH, O2, oxides of nitrogen, NOx, and then SO2, and also in the glucose. These are analytical type of sensors which are very much useful for testing glucose levels in the blood samples. So in that also these are having applications as a source of electrical energy, and also in making ion exchange membranes, which are used to have a controlled release of drug. In the preparation or in the manufacturing of ion exchange membranes also, these are having applications. And then in electrochromic displays and also in optical filters, these are having applications. And also in the manufacturing of photovoltaic cells, and also in electronic goods like LEDs and data storage equipments. So In all these kind of things, these polymer materials, conducting polymers are having lot of applicative part. So far in today's session, we have discussed what are conducting polymers, that is their introduction, and little bit of after introduction, how many types are there, ECPs and ICPs, intrinsically and extrinsically conducting polymers. Again, there is a subclassification for ICPs, that is conjugated ICPs, and the next one it is doped ICPs, and then ECPs again we have two different types. What are they? Conductive element filled ECPs, and then blended ECPs. So in the coming session, we are going to learn about biodegradable polymers, what is the specialty of biodegradable polymers, and a few examples. So that's all for today's class. Thank you.